Hi, welcome to AB Video 3.3a Part 1, Increasing and Decreasing Functions. Okay, so there's a lot of these questions on the AP. We're going to be looking at both when the functions we're looking at are increasing or decreasing, and we always look from left to right because that's as x is increasing. And when we say the function is increasing or decreasing, we mean the y's are increasing or decreasing. So when the y's are increasing, that means from left to right, the function is getting higher because the y's are getting bigger. If the y's are decreasing, then that means the function is getting lower. We're also going to be looking at the first derivative test for relative extra. So here's an example of some polynomial function. As you can see in the green is where the function is increasing or rising from left to right. And the blue is where the function is decreasing, or sorry, the red is where the function is decreasing from left to right. Now remember, when a function is increasing, that means its derivative is positive, because if you look at these slopes of the tangent lines all the way here from where the function's increasing, all of these slopes are positive. So when the derivative, it's back and forth. If the derivative of f of x is positive in an interval, that means f is increasing in that interval. And vice versa, if f is increasing in an interval, that means its derivative is positive in that interval. Here, when the function is decreasing, you can see that all the slopes are negative. So when the function f is decreasing, the first derivative is negative. Or vice versa, when the first derivative of f is negative, that means the function f will be decreasing. Okay, so f is increasing wherever f prime is positive, which means bigger than 0. F is decreasing wherever f prime is negative, which means when f prime is less than 0. So obviously, if we want to know where it's bigger than 0 or less than 0, we're going to start by finding out where it is 0. So to determine where, which are the x intervals, where f is increasing and decreasing, you start by finding the critical numbers of f of x. I.e., as you remember, the values of x in the domain of f, that's important, that make the first derivative 0 or does not exist, then you're going to put those critical numbers on a number line and do a pick and plug. Now, something the book never mentions, and that is you also need to include on that number line the vertical asymptote x values. So you really need to always look and see if there are vertical asymptotes. In exercises 1 and 2, it simply says use the graph of f. So they're giving you a graph to find the largest open interval. So these are going to be open intervals when we talk about f is increasing or decreasing, where the largest open interval on which f is increasing and the largest open interval on which f is decreasing. So here's the graph that they give you. So I've highlighted in red, as you can see, this is where the graph is decreasing because the graph is falling from left to right. And these are the two places, these green areas, is where the function f is increasing, i.e. rising from left to right. So you want to give the largest interval. So the largest interval where f is increasing is from 4 to 5, and then again from 6 to infinity. We're assuming here it just goes on forever. Where is f decreasing? It's decreasing from x equals negative infinity to x equals 1. It's decreasing from 1 to 4, and it's decreasing from 5 to, sorry, oh, that's wrong, from 5 to 6. Don't seem to be able to do that. Try that again. Okay, so this should be from 5 to 6. And, okay, it won't let me do that, but it will let me do this. All right, you will notice I cannot say that it's decreasing from negative infinity to 4, because if I said that, that would mean it's decreasing everywhere, including at 1. And of course, there's a vertical asymptote at x equals 1 here, so it's not decreasing, it's not doing anything there. There are no points there. Okay, so that's important. 3 to 8, use the graph. Again, they give you the graph, and this time they also give you the function to estimate the open intervals on which the function is increasing or decreasing. and then find those open intervals analytically. So because you've been given the picture, you can easily see the function is increasing from negative infinity to x equals -1, and then the function is decreasing from x equals -1 to infinity. So that's pretty straightforward. Now, to prove that analytically, remember we're going to be looking for the critical numbers, and we want the vertical asymptote. So the first thing we'll do is look at the domain of the function. So ignoring the actual graph, let's look at the function itself. It is a polynomial function, happens to be factored, so its domain is all real numbers. Its derivative will be -2 times x plus 1 to the 1 times 1. Hi, sorry about that. Okay, so analytically, what we're going to need to do is find the derivative, which of course is -2 times x plus 1 times 1. And we have to ask, we're looking for the critical numbers. So we have to ask ourselves, when does it not exist? When does it equal 0? Of course, it's a polynomial, so it's never not going to exist. And of course, it's going to equal 0 when x equals -1. At that point, what you need to do is you need to put that on a number line. Now, we know it's the entire number line because the domain's all real numbers. I'm going to take this critical number of -1, and actually, let me write down that is a critical number. So we're going to take that critical number, put it on a number line. You have to label your number line. This is crucial. You cannot have a bald number line and I don't know what's positive and negative or what's increasing or decreasing. So remember, we're trying to establish when the first derivative is positive or negative, which will help us decide whether f is increasing or decreasing, because that's the question. So now, when you are picking a number to the left of -1, such as -2, you will plug it. Leave this factored. Notice I did not multiply this out. If I replace x by -2, -2 plus 1 is negative, and negative times a negative is positive. I know the signs are going to alternate because this exponent here is 1, which is odd. But remember, you need the f prime, the f, the positive sign, the negative sign, the increasing, the decreasing. I put the 0 here because, of course, f prime of -1 is 0. That'll help later on when we're actually graphing. So again, you can see we get the same answer we got up above, which is f is increasing from -infinity to -1. F is decreasing on the interval for x goes from -1 to infinity. 9 through 16, they do not give you the graph. It's again asking the same question, identify the open intervals on which the function is increasing or decreasing. So here are the steps. First of all, what's the domain? And are there any vertical asymptotes? Then you're going to find the critical numbers. You know how to do that. You take the derivative, first derivative, ask yourself when is it 0 and when does it not exist. And as long as those numbers are in the domain, then those are critical numbers. You're going to take those critical numbers and the vertical asymptote values, x values. Let me write that down too. Well, obviously they're x values because it's x equals a number. And you're going to put those on the number line. Now, it could be a number array because there could be a built-in, t is bigger than 0, that kind of thing. Then you're going to determine where f prime is positive or negative, which of course will allow you to determine where f is increasing or decreasing. So for example, number 10. Well, for number 10, it's a polynomial function, so the domain's all real numbers. Critical numbers, we'll find the derivative, which is 27 minus 3x squared. Factor out the 3, factor the 9 minus x squared. Leave it in factored form. When does it not exist? Well, it's a polynomial. It never doesn't exist. When does it equal 0? As you can see, at x equals -3 and at x equals 3. Okay? Or you could take it from here and solve that equation slowly but surely. Be careful that you get plus or minus 3. That's why it's probably a good idea to factor it, and you'll see why it's a good idea to factor it anyways. So our domain was all real numbers, so both -3 and 3 are critical numbers. I have no vertical asymptotes, so I put my two critical numbers on a number line. It's a whole line. F prime F, you must label, Mabel. Now, and those are the two places where the derivative is 0, not as important right now. Now, you have these three regions. First of all, the exponents here for these factors are odd, which is why it's good to factor it, so you know the signs are going to alternate. So I really only need to pick one number. I'm going to pick 0, which is halfway between -3 and 3. If I plug in 0, I'll get a positive 0 plus 3 is positive, and 3 minus 0 is positive. So when I plug in 0, I get a positive, and then the signs alternate. And when f prime is negative, f is decreasing. When f prime is positive, f is increasing. When f prime is negative, f is decreasing. And therefore, as you can see, it's increasing on the interval from negative 3 to 3. It's decreasing from negative infinity to negative 3, union 3 to infinity. I want to point something out here. Let's just pretend this had been negative 27 plus 3x squared. You would have factored out a negative 3. You got to hang on to that negative 3 here, because when you plug these numbers in, that would end up being a negative times whatever times whatever. So do be careful. And that's the end of video 3.38, part 1.